Hey, do you remember the ratio test? It was a test for convergence where you're basically comparing a series to itself, the n plus 1th term over the nth term. You're kind of treating it as if it's geometric, where if that ratio, the absolute value of that ratio is less than 1, we know it converges. And that's exactly what the ratio test says, right? Right there. But if it's greater than 1, it diverges, and if it's equal to 1, we don't know anything. Why do I bring this up? Because pro tip for you here, that's exactly how you find the interval of convergence for a power series. So if we define a function in which every input goes into a series, and we want to know, does that series converge? Well, one of the ways to see if that series converges is to use the ratio test. Specifically, we're going to use it on the whole entire power series to find its domain, to find this thing that we're calling the interval of convergence. It looks like this. Looks just like the ratio test, but we only want to use one part of it. We only want to use the part for which we're guaranteed that the series is going to converge. So we want the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term to be less than 1. What is this u sub n business? Well, that's just the nth term of your power series. It looks like this. You remember this thing? So you're still just taking the ratio of the n plus 1th term here over the nth term, right? And you're forcing it. We're going to force it to be less than 1 because that, according to the ratio test, we're guaranteed convergence there. Now, one of the things that happens is that the ratio test is inconclusive at 1, so we'll have to test to see if that actually works. It's called testing the endpoints. You'll see that whenever we do a couple of these examples. But the biggest takeaway here is the fact that if we are going to find our interval of convergence, we just simply apply the ratio test. And if it converges absolutely, we know that it converges. Okay, so let's try that here on the first example here. What are the values of x for which the series, and you can see this is a power series because you got this variable x up inside your series, and we're multiplying that. Our coefficients are the factorials in factorial. Okay, all right. So what do? I'm going to just pretend like I'm taking the ratio test of this thing. I'm going to take the limit as n approaches infinity of the n plus 1th term over the nth term. Now notice that the index here is n, it's the variable n, so it doesn't affect this x that's right here, it's just the exponent on that thing. All right, so the absolute value of the n plus 1th term, everywhere there's an n, put an n plus 1 in it, so n plus 1 factorial, times x to the new exponent here is n plus 1 over just the original thing, the nth term, n factorial x to the nth. All right, now we're just going to simplify that. You don't set it less than 1. We're going to evaluate the limit and see where that limit, and that limit should be hopefully in terms of some sort of x there, and then we'll just see where that thing is less than 1. Okay, all right then. We can cancel stuff, I think, starting with this factorial. That's the wrong red. That's not the red I like to use. This n plus 1 factorial, I'm going to think of it as n plus 1 times n factorial, so I can cancel out my n factorials. And then I can do the same kind of thing on the variable x, right? So it's right over here. So x to the n plus 1th power divided by x to the n, you just subtract your exponents, x to the n plus 1 minus n, and your n's cancel, and you're just left with x. That guy has to stay inside of the absolute value bracket. So here, let me just keep writing stuff here. This is equal to the limit as n goes to infinity of the absolute value of just n plus 1 is left, and then times x. Okay, think about this for a second. This n here is going to infinity. This is a positive number, but we don't know anything about the x. Remember, that's the domain. We're trying to see what we can stick in for x. Maybe it's positive, maybe it's negative. So I got to keep the absolute value around the x, but not around the n plus 1. It can come out. So the limit as n goes to infinity of just n plus 1, and then we're going to multiply that times the absolute value of x. Okay, so what gets to change here? Well, the variable for the limit is n, If I plug infinity in here, this thing's just getting infinitely big, multiplying times x. It doesn't even matter what x is equal to. This is going to shoot off to infinity, which means that this thing diverges. It diverges for all values of x. And this is our saddest case here. The saddest case is the only thing that works is 0. It's going to contain 0. So like, for example, if I plug 0 in here, we're just multiplying everything by 0. It's going to collapse down to 0. And that's the only number that's in its domain. That's its whole entire interval of convergence. Here, let's look what that looks like. So here's this whole thing animated for us. It's equal to 0. So it diverges for all values of x not equal to 0. So why is that the case? Well, if this thing was, let's say, x was equal to 0, you have infinity times 0, which is L'Hopitalable, right? And then you would have to fix that limit. So we get to say that the only value for which this power series converges is its center point, x is equal to 0. That's case number 1. Again, like I said, it is the saddest case. Let's look at another one. So here is the next example for what values of x is the series from n equals 1 to infinity of 3 times x minus 2 to the nth power. And now notice that this one is centered here at 2 instead of at 0. No big deal. We're still going to apply the ratio test to it to see where it could possibly converge. All right, so I'm going to scroll down here a little bit. All right, so the limit as n goes to infinity, take the absolute value of the n plus 1th term over the nth term. Don't do anything to the x's. The only thing that's changing in this case is just the exponent. So this is 3 times x minus 2 to the n plus 1th term over 3 x minus 2 to the nth power. I said term, but I meant power. And then cancellation, boom, boom, right? And then this is just like I did before. These are the same base, x minus 2, same base, and we just subtract the exponents, and we're left with one factor of x minus 2 up top. This is equal to the limit as n goes to infinity of the absolute value of x minus 2. Now notice that there's no, like, the n's are completely gone. There's nowhere for me to stick infinity in here or any kind of number in here. And so the value of this limit is just simply the absolute value of x minus 2. If this series is going to converge, I want that quantity to be less than 1. I force it to be less than 1. And now we're pretty much almost done, but we got a little bit extra to do. So remember from, let's say from algebra, this is an and inequality, less the and. So to resolve this absolute value inequality, we're going to sandwich x minus 2 in between a positive and a negative 1. So I've got a negative 1 is less than x minus 2, which is less than a positive 1. Right? And then the next thing that I would do is I would just add 2 everywhere. So I can get x all by itself in the center. Add 2 to the right-hand side, I get 1. Add 2 to the right-hand side, I get 3. So there we go. This is the interval of convergence. Well, we're pretty sure this is the interval of convergence. The one thing that we don't know anything about is the number 3 and the number 1. And the reason why we don't is because it makes the ratio test equal to 1 instead of less than 1. Right? If I were to stick in the number 3 here, I get 3 minus 2, I get 1. And the ratio test fails at 1. Same thing happens right here. If I stick in 1, 1 minus 2 gives me a negative 1. Take the opposite value, it's 1. But I want it to be strictly less than 1. So what I have to do is I have to check these two endpoints. Before I do that, let's just, so that we can understand what's going on here for this interval. What we're saying is that any number in between here, if we plug it in here for x, it turns this into a series that converges to something. So let me just choose one. I'll choose something at random here, something in between, say, 1 and 3. How about, I don't know, like 1.5, so 3 halves. So I know, for example, that x equals 3/2 is inside here. So let's just plug that inside of this series and see what happens. So I have the infinite series, n equals 0 to infinity. Oh yeah, this is for x is equal to 3/2. Just to show you, just to illustrate, I would have 3 on the outside, and then this is 3/2 minus 2. That's your x minus 2 raised to the nth power. And now let's just kind of simplify stuff. 3 stays. And then I have, this is 1.5 minus 2. That's going to give me a -1/2, right? -1/2 raised to the nth power. Now, since this starts at n equals 0 to infinity, isn't that geometric? And our common ratio here is just -1/2. If you were to take the absolute value of that, that's less than 1, so it definitely converges. And you can find out what it converges to pretty easily because you have a sum formula for that. The first term, if you were to stick in 0, first term is just going to be 3 because that'll go down to 1. So it's a 3/1 minus your common ratio is this -1/2. That's right there. So I get 3/1 plus 1/2. That's 3/3/2, which I think makes the number 2, right? So, dividing by fraction, you multiply by the reciprocal, right? So, in other words, if you were to graph this thing, graph this point, you just made the point 3/2, 2 on your graph. All right. What we're saying is that anything in between these two numbers we're guaranteed is going to converge, but we don't know anything about the endpoints. Sometimes they converge and sometimes they don't. We just have to check them. So we're going to check our endpoints. As a matter of fact, checking the endpoints is often worth, if this is a free response question on the AP exam, is often worth one of the points that you do have to check it. Even if it doesn't work, still want to see that you check endpoints. Okay, so specifically, we're going to check when x is equal to 1, and we're going to plug that into our series, n equals 0 to infinity. We have the 3 on the outside. It would be x, which is my 1, minus 2 raised to the nth power. All right, inside of my parentheses here, that just makes that -1. 3 times -1 to the nth. And we are starting at 0, n equals 0 to infinity. So this thing is just alternating between a positive and a -3. It's 3 minus 3 plus 3 minus 3, and so on. This oscillates, so it diverges. What does that mean? That means x cannot be equal to 1. It's out of the domain. X equals, it can't be equal to 1. It's out. I say domain, but it's the interval of convergence. Sometimes this happens, but sometimes it works too. Sometimes you do get something that works at the endpoint. You just got to take it case by case and check your endpoints. Let's try the 3. Maybe this one's going to work. I got a good feeling about it. All right, n equals 0 to infinity. 3 on the outside, I get a 3 minus 2 on the inside. There's my x value. Raise it to the nth. Let's simplify here. 3 on the outside. 3 minus 2 just gives me 1 to the nth power. Oh, dang it. It didn't work either, because this one is just going to be a 3 plus 3 plus 3 plus 3. So this one's going to shoot off to infinity, which also diverges. So conclusion here is that x cannot be equal to 3. We didn't get our endpoints. That one is also out of the interval of convergence. How do you like how I spelled that? I don't even know if that's spelled correctly. Anyway, so that means that, if we had forgotten to check the endpoints, we still would have been okay, because our interval of convergence from 1 to 3 are the only values that work, not including 1, not including 3. So here it is all kind of played out here. Did the exact same thing I just did with you. You do have to check the endpoints. Make some sort of note. a reminder to check the endpoints, and then the next couple of slides just does that. So here you're checking the number 1. When that works, you just get positive and negative 3. Hey, this also diverges by the nth term test, apparently, according to my PowerPoint slide. Right, because the nth term is not going to be equal to 0, right? And then you check the 3, and you can conclude the exact same thing here. It's just a whole bunch of 3's. All right, so then that means that your interval of convergence is from 1 to 3. So here's our second case. The first one is that your power series converges only at its center point, whatever that center point is. The second one is that it converges over some sort of interval, and you get that interval with the ratio test. Our next one is going to be to figure out what that final case is. Stay tuned.